Okay, have a good day to every one of you. So in today's class, we are going to look at more models of activity coefficient. We will try to understand what is activity coefficient, how to find it. So let's try to Okay, so let's try to just have a look at what we learned in the last class. So in last class, we first started with Lewis Randall model, which states that fugacity of each species in ideal solution, it is proportional to its mole fraction, and proportionality constant is the fugacity of pure species. Now, and when this Lewis Randall model is valid, it is valid for valid in the particular cases when physical properties of molecules are similar, when low pressure, when gases behaves ideally at any pressures if component is in large excess, and it is usually valid for gaseous mixtures. These very two important things in liquid solutions when component molecules are similar in size and chemical structure. Those can be isomers, those can be adjacent members of homologous series and isotopically substituted compounds. Further, intermolecular interaction between unlike molecules are similar to those between like molecules. So let's say I'm having in one beaker water, in one beaker ethanol. So water will have some kind of interactions. Ethanol will have some kind of interactions. But when I'm mixing all these things together, so water ethanol interactions would be similar to those of water and ethanol. If these six things are followed, then we can say that we can use Lewis Randall model. Okay. Now we know that fugacity of vapor is Yi into P for low to moderate pressures, and for liquid it is Xi Pi set, where we consider Poynting correction factor as 1, and based on that we try to derive the from equilibrium condition vapor phase fugacity is equal to liquid phase fugacity, and from there we try to find the Raoult's law, which is Yi into P is equal to Xi into Pi set. And when we plot fugacity versus fugacity of component I in mixer versus Xi, we see that when Xi tends to 1, this curve follows linearity, and the proportionality constant is nothing but fugacity of pure component in solution. And when it is Xi tending to 0, then also it is following linearity, but in this case linearity constant is not fugacity of component I in mixer, pure component I in mixer, but it is Henry's constant Hi, which is called ideal dilute solution. Okay, now further we try to look at characteristics of ideal solution, which are summation of this delta Vm is equal to 0. It means when I am mixing two ideal solutions, there will be no change in volume. Further, there will be no change in enthalpy, meaning component mix with no absorption or evaluation of heat in case of ideal solution. Then there is no change in internal energy in case of ideal solution. And for Gibbs free energy, it is RT summation Xi ln Xi, and entropy is minus R summation Xi ln Xi. Okay. So we know that delta H mixing is equal to 0. So what does this say? This says that, okay, ln xi is always less than 1. So ln xi is always going to be less than 0. So this whole summation negative is going to be positive, and delta Sm is always going to be greater than 0. So this says that solution forms or component mixes because of entropic effect, not because of the enthalpic effect. Now how to identify if the solution is ideal or not? So we plot Pi versus Xi, and we see that if it is linear, Pi meaning P1, P2, P1, P2 and total P. When we plot versus Xi, so we see that when Xi tends to 0, it should be P2 set. When X1 tends to when x1 tends to 0, it should be P2 set. When x1 tends to 1, it should be P1 set, and this is total P. And total P expression is nothing but this P1 set minus P2 set into x1 plus P2 set. So we see that this all should follow linearity. If they are following linearity, then we can see that our solution is ideal solution. And then we had a look at PXY diagram. If you remember, in PXY diagram, we started with a particular point. Let's say here we try to reduce the pressure. So there will be one point when first droplet of liquid will convert into vapor, and that point is called bubble curve. And for family of these curves, family of these points, when we connect them, it becomes bubble curve. Then further increasing pressure, our vapor and liquid will be in equilibrium. And at one point, there will be last droplet of liquid that is remaining to convert into vapor phase, and that is called dew point. And family of these points are called dew curve. And further reducing the pressure, we will be at vapor phase. Similar thing, we can see that let's say I'm starting from here, and if I'm increasing pressure, so there will be first dew formation, that is called dew point curve. Then liquid and vapor will be in equilibrium, and then further increasing, the last droplet of vapor will be left to convert into liquid phase, that is called bubble point. And family of curves are known as bubble point curve. And further increasing pressure, we are at pure liquid phase. Similarly, TXY diagram also we studied. Let's say I'm at this point, I'm increasing the pressure. Sorry, I'm increasing the temperature. So what is going to happen? Component will remain in liquid phase until it reaches at boiling point. So at one point where first droplet of liquid is going to be converted into vapor phase, that is called bubble point curve. Further increasing temperature, we will be having vapor liquid equilibrium. And then further increasing temperature, we will be at one point where there will be last droplet of liquid that is going to be converted into vapor phase, that is called dew curve. And further increasing temperature, we will be pure vapor zone. Okay. So this is what we studied about this PXY and TXY diagram. So let's say if I am given temperature and any mole fraction. So what can I do from temperature? I can find out the vapor pressure of components from Antoine equation or so. So if I know the vapor pressure, then I can find P1 is equal to X1 P1 set, P2 is equal to X2 P2 set, and from there I can find total pressure P, and from total pressure P I can find Y1 and Y2. Okay. Okay, so this distillation concept also we studied, relative volatility, that is defined as P2 set divided by P1 set. Okay, so P2 set by P1 set, P2 by P1, if I divide these two equations, so P2 by P1 is equal to X2 by X1, P2 set by P1 set. Okay, and when I try to simplify this equation, I find that alpha is equal to Y2 by Y1 divided by X2 by X1. Component 2 in vapor phase divided by its mole fraction in liquid phase. Component 2 mole fraction in vapor phase divided by component 1 mole fraction in vapor phase divided by component 2 mole fraction in liquid phase divided by component 1 mole fraction in liquid phase. This is similar to something called selectivity, which is used in liquid extraction. So this y, we can say that y is equal to alpha into x divided by 1 plus alpha minus 1 into x. Now from here we had a look at bubble point and dew point computations. So we know that for first bubble composition, how can I say y1 is equal to, if I am following ideal solution, so y1 is equal to x1 into p1 set by pb, that is bubble pressure. So summation of yi should be equal to 1. So this leads to us as xi, summation of xi into pi set will give me bubble pressure. And similarly for first dew composition, dew pressure will be 1 upon summation of yi divided by pi set. So this will give me dew pressure. Okay. So this is what we did in last class, and we had looked at some very simple problems. Okay, then we had a look at this flash calculation. Yeah. So for flash calculation, what we did, we have some composition in feed, and we are trying to flash it. So vapor and liquid we are going to obtain with yi and xi's. Okay. Then when we apply, we define this one more very important quantity, that is called partition coefficient. How it is partitioning between vapor and liquid phase, yi divided by xi. Okay, so based on that, my yi into p is equal to xi into pi set. So yi by xi is equal to pi set by p is equal to ki. So we know that, let's say I'm dealing at some temperature and pressure will be of system will be known. So I want to do it at let's say 373.15 Kelvin and 1 atmospheric pressure. So temperature, pressure is known, and from temperature is known. So from that temperature I can find pi set. So ki values are always known. Now if we apply overall mole balance and component mole balance, we are left with some kind of equation, that is yi is equal to zi into ki divided by 1 plus v ki minus 1, where we assume that our feed f is equal to we have considered mole basis 1 mole feed. Basis was 1 mole feed. So now we know that we can replace uh, xi, and we can find from yi xi is equal to yi by k. I can do that, but constant here is summation of yi should be is equal to 1. So what I need to do, I need to assume some different values of v, and we need to see that if that equation satisfies this whole summations is equal to 1 or not, that I need to satisfy. And this is very easy thing to understand. Ki is equal to yi by xi. So if ki is greater than unity, this means that component or species I, it exhibits higher concentration in vapor phase, and when Ki is less than 1, it exhibits higher concentration in liquid phase. It is not vaporizing basically. Okay, so this is what we studied in last class about ideal solution. Then we moved from ideal to non-ideal solution, and for for case of non-ideal solutions, we know that delta Vm, mixing of the change in volume, when we mix it, it is not is equal to 0. Delta Hm is also not 0, and delta Um is also not equal to 0. So this P1, P2, and PPIs versus X curve, Xi's that we find, that does not vary linearly. Okay, so there are two cases. It can increase. Let's say P total is greater than that is estimated from ideal Raoult's law, and in other case P total is this green curve less than what is obtained from Raoult's law. So green curve says that higher P1, P2, and P than in ideal solutions, that is estimated from Raoult's law. So in this case, more we are getting more pressure. More pressure meaning more components are going in vapor phase. What does this mean? That mean that interactions when we are forming a solution AB, it is always less than A and AB. So it has high tendency to go to vapor phase, and this shows the positive deviation from Raoult's law. In this case, gamma I is greater than 1. In other case, this is the second case, uh, lower P1, P2, and P than ideal conditions. So lower pressure meaning it has lower tendency to go into vapor phase. So what does this mean? Lower tendency meaning now after forming the solution, they are more tightly bound. So AB interactions are more than AA and BB interaction, and this is called negative deviation from Raoult's law. In this case, gamma I is less than 1, not less than 0. This is a mistake. It is less than 1. Okay. Now, how can we now deal with this non-ideality, positive or negative deviation from Raoult's law? So the equation was proposed by Laar. So that equation is P2 is equal to x2 into P2 side exponent of 1 minus x2 whole square delta U naught by KB, where KBT, where delta U naught is our interaction energy, that is difference between AA, BB, and AB. So when I am dealing with ideal solution, what is this? Delta U naught is equal to, it is going to be equal to 0. So interactions between like and unlike molecules will be similar. So in this case, this exponent, this term is 0, so exponent of 0 is 1, and we will be left with our Raoult's law, that is P2 is equal to x2 into P2 side. That was ideal solution. So there will be one more case where delta U naught is greater than 1. So that shows positive deviation from Raoult's law, and unlike molecules attract more weakly as compared to like molecules. So that's why uh, this P2 will be equal to x2 into P2 side into some additional term that is greater than 1. So P2 will be my higher value than x2 into P2 side. Similarly, when delta U naught is less than 1, so we see negative deviation from Raoult's law. So unlike molecules attract more strongly as compared to like molecules. So if this term is less than 0, so exponent is going to be less than 1. So this P2 will be reduced. P2 will be less than x2 into P2 side. Okay, so we know that when we were dealing with vapor phase, so PV is equal to RT, that was for ideal gas, and PV is equal to ZRT, that was for non-ideal conditions. Similarly, when we are dealing with liquid phase, ideal liquid phase solutions, that is given by Lewis-Randall model. So Fi cap, fugacity of component I in mixture or in solution, is equal to Xi into its pure component fugacity Fi. That is for ideal solution. So for non-ideal solution, we add here one more term like Z we added for vapor phase. We add here gamma I. for liquid phase, that represents non-ideality of solution. That's gamma is a correction factor which is known as activity coefficient. And we know that for non-ideal solutions, this delta Vm can be greater than zero, and or this can be less than zero. So if our solution were ideal, so we will have um, this term delta V mixing is equal to zero, but in our case, solution is not ideal. So what we define one more property that is called excess property. The solution exhibits because of the non-ideality of solution, that is defined as its real value minus its value if it were ideal. Okay, so this excess property we will have a look further. So let's try to first understand what will be now my modified Raoult's law when I am adding correction factor gamma I. Okay. So, okay. Okay, let's first try to go through basics for derivation of Raoult's law. So we know that fugacity of component I in vapor phase is equal to fugacity of component I in liquid phase. So phi I cap was equal to Fi V divided by Yi into P, and gamma I was Fi cap L divided by Xi into Fi L. So we find Yi into P into phi I cap is equal to Xi into gamma I into Fi, fugacity of component I in liquid phase. Okay, now vapor phase is generally considered as ideal. So phi I cap will be is equal to 1, and pointing correction factor when we are dealing with low to moderate pressures. So this for this term also pointing correction factor will be 1. So we can replace FIL with PI set. So we will left with our modified Raoult's law, that is Yi into P is equal to Xi into gamma into Pi set. So we are having one additional term, that is activity coefficient. Earlier when we were dealing with ideal solution or ideal conditions, so it was Yi into P is equal to Xi into Pi set. But when we incorporated non-ideality, we need to add this one more term, that is gamma, and we need to remember that gamma is a very strong function of temperature. Okay, and this is called this equation 9, or this phi into P is equal to Xi into gamma into Pi set. This is known as modified Raoult's law. The law results when gamma I is introduced into Raoult's law. Okay, so if I put gamma is equal to 1, that is ideal solution, we get back to our original Raoult's law. Now, for ideal solution, we had this bubble point calculation that PB is equal to Xi, summation of Xi into Pi set. We just had a look at that part. So similarly, in this case also, how can I find bubble point? So this constraint is summation of yi is equal to 1. So earlier what was my yi? Yi was xi into pi set by pb is equal to 1. So I found pb is equal to summation xi pi set. But in this case, or when I am dealing with non-ideality, so I am having one more additional term, that is gamma I. So I need to incorporate that from modified Raoult's law. So we see that bubble point pressure PB is equal to summation of xi into gamma I into pi set. So now in each calculation, I need to additionally find out what is the value of activity coefficient at each temperatures. Okay. Similarly, so when I am writing this for binary system, I can write that PB is equal to x1 gamma 1 P1 set plus x2 into gamma 2 into P2 set. Okay. Similarly, for dew point calculation, we know that summation of xi is equal to 1. So from there we find in ideal case that 1 upon PD dew point pressure is equal to 1 upon summation of yi by pi set. But here we are having one more additional gamma term. So PD will be equal to 1 upon summation of yi divided by gamma I into pi set. So for binary system, I can write it down as PD is equal to 1 upon y1 by gamma 1 p1 set plus y2 divided by gamma 2 into p2 set. Okay. Now, this was all about bubble point and dew point calculations when I am dealing with non-ideality of the system. Now further, let's say I'm looking at the flash calculations that I just showed it to you. So K is always going to be Yi by Xi. How a component is partitioned between vapor phase and liquid phase. This similar term partition coefficient is also used in liquid extraction when we are having extract and definite, and when we are saying that how solute is partitioned between solvent rich phase and the actual original solution. Okay. So this is similar term Ki is equal to Yi by Xi. And so our modified Raoult's law is Yi into P is equal to Xi gamma I pi set. So yi by xi will be equal to gamma I pi set by p, which is equal to ki. Earlier ki was just pi set by p, but in non-ideality we are introducing one additional term, that is gamma I. So what do I need to do? Let's say I know the flash is done at some temperature pressure conditions. Okay, so pressure is always known, temperature is known to me. So from that temperature I can find out the value of vapor pressure using Antoine equation, and for that particular temperature, whatever expression of we are having, from there we can find out the values of activity coefficient. So yeah, so this is how we can do it using modified Raoult's law, and we need to change these terms. Okay. Now we have in the ideal part, we did not had a look at that thing. Wait, if it is there, I can show it to you. This is Henry's law, flash calculation. No, it is not there. Okay. So azeotropic condition also I can study. So when does azeotropic condition occur? So this is my this is my azeotropic point where my y is equal to x. So in this case, my alpha will be equal to relative volatility will be equal to 1. So azeotropic condition occurs when relative volatility alpha is equal to 1. So at azeotropic condition, no separation takes place. So I have alpha 1 2 is equal to y1 by x1 divided by y2 by x2. We have derived this. So from modified Raoult's law, how can I replace y1 by x1 and y2 by x2? So y1 into p is equal to x1 gamma 1 p1 set. So y1 by x1 is equal to gamma 1 p1 set by p, and y2 into p is equal to x2 gamma 2 p2 set. So I can replace y2 by x2 as gamma 2 into p2 set by p. So if I put this term into this equation, so I can find alpha 1 2 as um this gamma 1 p1 set divided by gamma 2 p2 set. Okay, so when we were dealing with ideality, what did we find? We just see that alpha was ratios of saturated pressures, but when we are dealing with non-ideality, we need to add activity coefficient of each component. Okay, so we know that at azeotropy alpha is equal to 1. So I can write down gamma 1 by gamma 2 is equal to P2 set by P1 set. So what does this say? This says that if I somehow, I always know the temperature condition. So from temperature, I can find out the, from Antoine equation, I can find out the values of P2 set and P1 set. So that will give me one correlation between gamma 1 and gamma 2. Okay. Now, we are left with one very important thing, that we are continuously discussing about activity coefficient we need to include, but how to find out or how to estimate the value of activity coefficient, that is not we are looking right now. So let's have a look at that part. So before looking at activity coefficient part, let's have some discussions on excess properties. So we had looked at what is excess property. Excess property is because of non-ideality of the solution. This excess property solution is having because of the non-ideality. If the solution were ideal, I would have delta V mixing is equal to 0, delta H mixing is equal to 0, delta U mixing is equal to 0. But because of non-ideality, solution will not have delta um is equal to 0, delta vm is equal to 0, and delta hm is equal to 0. So if that is not 0, that means solution is exhibiting some kind of excess property because of this non-ideality. So excess property is defined as m excess is equal to m real minus m ideal. This is similar to what we learned in case of vapor phase, where we defined the departure function as actual um, property minus property if the gas were ideal. This thing we learned earlier. So this is similar to departure function, but when we are dealing with vapor phase, we call it departure function, and when we are dealing with liquid phase, we call it excess property, and that has a meaning. Why the word excess property? Because of delta um is not 0, delta vm is not 0, delta hm is not 0. So that non-zero is something excess for the system. So that excess property is 4. That's why it is generally defined for liquid phase. Okay. So V excess is equal to V actual minus V ideal. So what will be V actual? It will be summation of Xi into Vi bar. Okay. partial property of component I in solution or in mixer, whatever you want to call it. So summation of xi into vi bar minus for this vi ideal. So that is summation of xi into v ideal. Okay. So I can just write it down as summation of xi vi bar minus V ideal, meaning property of molar volume of component I in mixer minus its volume if it were behaving ideal. So that will give me some delta um, and this will not be equal to 0 in case of non-ideal solution. Okay, similarly in case of excess enthalpy, so that is H actual minus H ideal. So H actual is given as summation of Xi into Hi bar minus Xi into Hi, or I can just write it down as Hi. Okay, so I find that it is summation of Xi Hi bar minus H ideal, that is equal to delta H mixing, enthalpy of mixing. It can be absorbing or it can be releasing heat. Okay, similarly in case of U, internal energy, excess internal energy is U actual minus U ideal, and from there we find that summation of Xi Ui bar minus U ideal, that is equal to delta U mixing. Okay, now similarly Gibbs free energy G excess is equal to G actual minus G ideal. Okay, so Xi into Gi bar minus Xi into G ideal. Okay, so G ideal is something. G ideal is something we had looked in last class, that was summation of xi RT into summation of xi ln xi. This thing, if you remember, RT summation of xi ln xi. This will be in case of ideal delta G mixing when it is ideal, but it is not ideal. It is real. It is not following ideality. So what do I need to do? I need to find out what is Gi bar. So yeah. So this term Gi bar. So let's try to find out partial molar this term. So which will be equal to Gi bar. Excess will be equal to Gi bar minus Gi minus Gi bar minus Gi if it were ideal. Okay. So what is Gi bar minus Gi? So Gi bar minus Gi can be written as RT into summation of ln Fi cap by Fi. This we have already studied. Okay. Now Fi cap I can replace it with, in case of ideal solution, I will have Fi cap is equal to xi gamma I into Fi. So Fi cancels out and I will have Gi bar minus Gi is equal to RT into summation of ln xi gamma I. So it will be Gi bar minus Gi will be equal to RT summation of ln xi plus RT summation of ln gamma I. Okay. Now in the ideal case solution, what is it going to be? Gi bar minus Gi in case of ideal. So in case of ideal, gamma I is equal to 1. So ln 1 is 0. So this term goes out. So we are only left with RT into summation of ln xi in case of Gi bar minus Gi. Then we are dealing with ideality. Okay. So G excess, I can just write it down. G excess as this term RT summation of xi ln xi plus RT summation of xi ln gamma I. These terms RT summation of xi ln xi, RT summation of xi ln gamma I. Wait. Let's not go to this route. Okay, so we have these two terms, right? This term and this term. So what is will be my excess Gi bar excess? Gi bar excess will be is equal to this term minus this term. So I will be only remaining with RT into summation of ln gamma I. That will be my Gi bar excess RT ln gamma I. For each component, let's say I am writing just for component, but it is RT ln gamma I. So for multi-component, Gi bar excess actual minus ideal So this term minus this term, so I'm only left with RT into summation of ln gamma I. So that is my GI bar excess. And similarly, how can I find actual property? It is just Xi into GI bar. So it will give me GE by RT, that is summation of G is equal to summation of RT summation of Xi ln gamma I. This thing also we have learned the way we define partial molar property. So the total property Gxs will be equal to summation of Xi into Gi bar in case of everything except fugacities and fugacity coefficient. This also we have studied in last class. Okay. Okay. So this is Gi bar by RT, that is ln gamma I, summation ln gamma I, and Ge by RT, that is summation of Xi ln gamma I. Okay. Now similarly we can find out this excess property in case of entropy. So S minus S ideal, S delta S mixing in case of actual conditions minus delta S mixing in case of ideal condition. So in ideal condition, we have found out that delta S mixing is minus R summation of Xi ln Xi. So this term is nothing but minus R summation Xi ln Xi. So this turns out to be Se is equal to delta S mixing plus R summation of Xi ln Xi. Okay. Okay. So now let's try to, when we were dealing with fugacities, we try to understand the effect of temperature and pressure on fugacities of each component. So let's try to do the same thing in case of, let's try to do this same thing in case of this gamma I also. So how can I understand the effect of gamma I on temperature and pressure? Okay, so let's try to do this. So we know that this Lewis-Randall model in case of non-ideal solutions, it is nothing but Fi, fugacity of component I in liquid phase is equal to Xi gamma I FIL. So Fi cap L divided by FIL is equal to Xi into gamma I. If I take ln on both sides, it is ln Fi cap by Fi is equal to ln Xi gamma I. So if I break this, so it is ln Xi plus ln gamma I. Okay. We know that del P of ln Fi cap by Fi at constant temperature is VIL minus Vi by RT. Okay. So this term is nothing but ln Xi plus ln gamma I. This term is ln Xi gamma I, which is nothing but ln Xi plus ln gamma I. Now we know that composition is not going to change with pressure. Composition will be fixed. So this ln gamma I turns to be cancelling. So we know that del ln gamma I by del P is equal to Vi bar minus Vi by RT, which is nothing but Vi bar excess divided by RT. Vi bar excess is excess molar volume of component, excess partial molar, this bar meaning partial property, right? So excess partial molar volume of component I, so which is nothing but actual molar volume of component I in the system or in the solution minus molar volume of component I in the ideal solution at same temperature and pressures. Okay, so this is nothing but Vi bar excess. Okay, so this was the effect of pressure on activity coefficient, that is Vi bar excess divided by RT. Now let's try to have a look at the effect of temperature. So we have this del ln Fi by del T is equal to Hi naught minus Hi by RT square, and del ln Fi cap by del T is equal to Hi minus Hi bar divided by RT square. When we are dealing with solution, this Hi will be replaced with Hi bar. Okay. So del ln Fi cap by Fi will be is equal to, this is negative minus signs. Okay, so it will be Hi minus Hi bar divided by RT square, which is nothing but Hi bar negative of Hi bar excess divided by RT square. Okay, so what is this ln Fi cap by Fi? This we had a look. Fi cap by Fi is equal to Xi gamma I. So if I take ln, so it is ln Xi plus ln gamma I. And when I am trying to differentiate this equation with respect to temperature, so we know that composition is not going to change. The feed it is not going to change with temperature. Okay, so this term is going to be cancelling out. So we are only left with ln gamma I. Okay, so del T of ln gamma I at constant pressure is nothing but minus of hi bar excess divided by RT square, which is nothing but partial molar excess enthalpy of any component I. Okay, so this is what we studied about effect of temperature and pressure on activity coefficient. Okay, so we see that we defined this GI bar excess, which is nothing but RT summation ln xi ln gamma I, and GE actual property G access is equal to summation of xi ln xi. And we try to understand the effect of activity coefficient, effect of temperature and pressure on activity coefficient. So we find that del ln gamma I by del P is equal to Vi bar excess divided by RT, and Vi bar excess is actual excess partial molar volume of component I, which is nothing but actual molar volume of component I in solution minus molar volume of component I in ideal solution. So these two should be estimated at same temperature and pressure. Okay, and we find out that del T of ln gamma I at constant pressure is equal to minus hi bar excess divided by RT square. Okay, so now okay, so till now we have looked at Gibbs-Duhem equations in all various cases, single component system, multi-component system. We studied Gibbs-Duhem equation in terms of partial molar properties also. In terms of excess property, similar thing can be written. So what can we write in terms of activity coefficient? Okay, so first let's try to have a look. Okay, so let's first try to have a look at for the single component system, the Gibbs-Duhem equation of S dt minus V dp plus N into d mu is equal to 0. For multi-component system, so it was just Ni into d mu I. So in terms of partial molar properties, it was Xi into we have mu I cap this component I in mixture. Then in terms of excess molar property, I can just write it down as mu I can replace it with GI bar excess. Okay, so now let's try to replace this GI bar excess in terms of activity coefficient. So we know that we just find out that GI bar excess is nothing but RT into ln gamma I. Okay, so if I replace this SE dt minus VE dp plus XI differential of RT ln gamma I is equal to 0. So I will have SEDT minus VEDP plus summation of, okay, R is not going to change. So we have two terms, temperature and gamma, which I can differentiate. So summation of Xi into R, this remains constant. Let's say I'm keeping gamma I constant, ln gamma I constant. So I will have dt term plus second time I'm keeping temperature as it is, Xi RT differential of ln gamma I will be equal to 0. Okay, so this is my Gibbs-Duhem equation. Now let's try to simplify it. So what can I write? I can write that Sxs is equal to Sxs is equal to Hxs minus Gxs divided by T. Correct? And Gxs divided by RT is nothing but summation of Xi ln gamma I. Correct? Gxs by RT is equal to summation of Xi into ln gamma I. Yeah. So what can I do? I can write it down SEDT. Yes, I can write it down SEDT is equal to HE by T dt minus GE by T dt. So what is GE by T? GE by T is summation of Xi ln gamma I into R. GE by T is R into summation Xi ln gamma I into dt is equal to 0. Okay. So I'm just writing in terms, I'm just multiplying with dt. So what can I replace now? SEDT, I can replace it with this term. HE by T dt. Okay, I should not write down 0 here. It should be just this term. SEDT is equal to HE by T dt minus R summation of Xi ln gamma I dt. Okay. this 0 should not be here. Okay, this term can't be here. Okay, so now we know that HE, this SE dt is HE by T dt minus R summation xi ln gamma I dt minus this term remains as it is minus VE dP plus R. R is constant, so I am keeping R outside. So R xi ln gamma I dt plus here RT is constant, so xi d ln gamma is equal to 0. This whole term is nothing but going to be is equal to 0. Okay. So if I simplify this, so this term and this term, these two are similar. So this cancels out. So we are only left with He by T dt minus VE dP plus these two terms are cancelled out. So we are only left with this RT summation xi d ln gamma is equal to 0. So this equation is called Gibbs-Duhem equation in terms of activity coefficient. Okay. So from here, SEDT minus VEDP plus summation xi d gi bar is equal to gi bar xs is equal to 0. From here, we derived this equation in terms of activity coefficient, which is nothing but He by T dt minus VE dP plus RT into summation xi d ln gamma is equal to 0. Okay. Now let's say I'm dealing with constant temperature and constant pressure. So at constant temperature and constant pressure, this term is going to be 0. This term is going to be 0. So we are only left with this term RT into summation xi d ln gamma is equal to 0. RT term is not 0, so we are only left with summation of xi into differential of ln gamma is equal to 0. So this is Gibbs-Duhem equation in terms of activity coefficient. Yeah, in terms of activity coefficient at constant temperature and constant pressure. Okay. So there is one another way to derive that equation. But before that, we should understand this whole all differences. First, we deal with single component system. Then we dealt with multi-component system and we wrote in terms of partial molar properties. And then we wrote this equation in terms of excess property. And from excess property, we try to convert it in terms of activity coefficients. Okay. So okay, so this is Gibbs-Duhem equation at constant temperature pressure in terms of activity coefficients. Okay, so now let's try to move ahead. There is one more way to derive this Gibbs-Duhem equation in terms of this activity coefficient. So at constant temperature pressure, we know that this summation xi d mu I cap is equal to 0. So mu I cap, I can replace it with ln fi cap, and fi cap is nothing but xi gamma I into fi from Lewis Randall model with including non-ideality gamma I term. So we are left with summation of xi differential of ln gamma I xi gamma I fi is equal to 0. So if I break this term, xi d ln xi plus xi d ln gamma I plus xi d ln fi is equal to 0. So when we are dealing with constant temperature pressure, this term is not going to change, right? So this is going to be constant, and similarly when we are dealing with constant temperature pressure, so fugacity of component I in pure state at that temperature pressure is not going to change. So this term is also going to be 0. So we are only left with summation of xi into d ln gamma I is equal to 0. Okay, so this is called Gibbs-Duhem equation. So at constant temperature, if I want to write it down, only constant temperature. Okay, so at constant temperature, this term is going to be 0. So we are only VEDP is equal to RT summation xi d ln gamma I. VEDP is equal to RT summation xi d ln gamma I. And when I am dealing with constant pressure, so this term is going to be 0. So we are left with He dt is equal to RT square. He dt is equal to minus RT square. He dt is equal to minus RT square summation xi d ln gamma I. Okay. So this is all about Gibbs-Duhem equation, and Gibbs-Duhem equation is really a very important phenomena. Uh, okay, so we derived this equation as xi summation of I xi d ln gamma is equal to 0. This is my Gibbs-Duhem equation. Okay, so for binary solution, what can I write? I can write it down as x1 differential of ln gamma 1 plus x2 differential of ln gamma 2 is equal to 0. Okay, for binary components, I put I is equal to 1 to 2. Okay, so I will have x1 differential of ln gamma 1 plus x2 differential of ln gamma 2 is equal to 0. Okay, so I can write it down as x1 del ln gamma 1 by del x1 at constant temperature pressure plus x2 del ln gamma 2 by del x1 at constant temperature pressure is also equal to 0. Okay, this is what I can write down. Now, what can I see? I can see that del ln gamma 1 by del x1 at constant temperature pressure is equal to, if I make this subject, so I will have minus x2 by x1 del ln gamma 2 by del x1. Okay. So from Gibbs-Duhem equation 4, we will only talk mostly about binary solutions. So we have this term x1 differential of ln gamma 1 plus x2 differential of ln gamma 2 is equal to 0. And from there I wrote this x1 del ln gamma 1 by dl x1 at constant temperature pressure plus x2 del ln gamma 2 by del x1 at constant temperature pressure is equal to 0. Okay. And okay, so we are left with this equation del ln gamma 1 by del x1 at constant temperature pressure is equal to minus x2 by x1 del ln gamma 2 by del x1 at temperature pressure. Now I know that x1 and x2 are not independent. If I fix x1, x2 is automatically fixed. So x1 plus x2 is equal to 1. We know that constraint. So dx1 plus dx2 will be equal to 0. So I can say that dx1 is negative of dx2. So I can replace this dx1 with negative of dx2. So I'm left with del ln gamma 1 by del x1 at constant temperature pressure is equal to x2 by x1 del ln gamma 2 by del x2 at constant temperature pressure. Okay. So this is very important thing to know, that let's say if I am knowing gamma 2, I can automatically, if I know that how gamma 2 is varying with its composition x2, I can automatically find out how gamma I varies with composition x1. Okay. So we say that slope of ln gamma 1 versus x1 is opposite to this ln gamma 1 versus x1 is opposite to the slope of ln gamma 2 versus x1. These slopes are opposite, right? It is just negative sign. This y is equal to mx. No, sorry. Yeah, so there is only the difference of this minus x2 by x1. So that's why we are saying that slopes are opposite. Okay. Now we know that when x1 tends to 0, component 1 is in infinite dilution. So what does that mean? Automatically this means that x2 is tending to 1. Correct? x2 is tending to 1. When x2 is tending to 1, so gamma 2 also tends to 1 and ln gamma 2 tends to 0. Okay, so basically how can you understand this? Let's say this x1 term is here, x1 by x2 is written like this. So when x1 tends to 0, so this whole term, let's say this, I will have equation minus x1 by x2 del ln gamma 1 by del x1 is equal to this del ln gamma 2 by del x1 at constant temperature pressure. Okay, so now I'm saying that x1 is tending to 0. So this term is going to be 0. So I'm only left with this term del ln gamma 2 by del x1 is equal to 0. Okay, so del gamma 2 is tending to 0. Del gamma 2 is tending to 0, meaning gamma 2 is tending to 1. So when other component, one component is in very excess quantity or other component is in very dilute nature, so is always tending to 1. So this shows the solution will try to behave ideally. correct? Because gamma 2 is tending to 1. Similarly, let's say x2 is tending to 0. Earlier x1 was tending to 0. Now let's say x2 is tending to 0. So this whole term is going to be 0. So we are only left with ln gamma 1 is tending to 0. Ln gamma 1 is tending to 0, meaning gamma 1 is tending to 1. So when one component is in excess quantity to other, so we can say that it is behaving ideally. The other component is behaving ideally in the solution. Okay, the component in excess quantity is behaving ideally. Okay, now from this equation, del ln gamma 1 by del x1 is equal to minus of x2 by x1 del ln gamma 2 by del x1. What can I write? Del ln gamma 1. Ln gamma 1 can I write 1 upon gamma 1 d gamma 1. Similarly, x1 by gamma 1. So it was x1, x1, x1 will be here. Let's say x1 del ln gamma 1 by del x1. So x1 into del ln gamma 1, I am replacing it with 1 upon gamma 1 d gamma 1. Correct. So x1 by gamma 1 d gamma 1 by dx1 is equal to minus x2 del ln gamma 2 is 1 upon gamma 2 d gamma 2. So minus x2 by gamma 2 d gamma 2 by dx1 at constant temperature pressure. Okay. So these also we know that when x2 tends to 0, so this term ln gamma 1 tends to 0. So when x2 tends to 0 or x1 tends to 1, x2 tends to 0. So this 1 upon gamma 1 d gamma 1 by dx1 is equal to 0. So gamma 1 versus x1, it is having one horizontal slope as x1 is tending to 1 or x2 is tending to 0. Correct? So I told that if I know gamma 2, how gamma 2 varies with x2, I can find how gamma 1 varies with x1. Okay, so let's try to prove it. So x1 dln gamma 1 plus x2 dln gamma 2 is equal to 0. So I can write dln gamma 2 is equal to minus x2 by x1 dln gamma 1. Okay, so when x2 is equal to 0, 2, x2 is equal to some value. So ln gamma 2 at any x2 minus ln gamma 2 at x2 is equal to 0. Yeah. When x2 is tending to 0, other component is in excess quantity. So that is something going to behave ideally. Okay, so ln gamma 2 at x2 minus ln gamma 2 at x2 is equal to 0 is equal to minus x2 is equal to 0. So 0 to x2 minus x1 by x2 dln gamma 1. So we can find gamma 2 from values of gamma 1. If I know gamma 1, so I can correlate it and I can find the values of gamma 2. Okay, so this was the whole point of this thing. Okay, so now let's say uh, we are just talking about we can find gamma 2 from gamma 1 from gamma 2. Okay, but what is the expression that we are having for activity coefficients, right? So let's say I am writing one expression that is ln gamma 1 is equal to a into x2 square. That is one kind of expression I am writing. Okay, so let's say ln gamma 1 is equal to a x2 square. So in terms of x1, I can write it down as ln gamma 1 is equal to a, x2 is equal to 1 minus x1 whole square. Okay, so d ln gamma 1, this equation, original equation we had d ln gamma 1 by dx1, this equation, sorry, d ln gamma 1 by dx1 is equal to minus x2 by x1 dln gamma 2 by dx1. This was the original expression we had. Okay, so what is dln gamma 1 by dx1? So if I differentiate this, a is constant, so 1 minus x1 square, so it is 2 1 minus x1, and minus x1 is minus 1. So we have this term minus 2a into 1 minus x1 is equal to minus x2 by x1 ln gamma 2 by dx1 d ln gamma 2 by dx1. So I am left with c1 minus x1 is nothing but x2. So this x2 cancels out, minus 1 cancels out. So I am only left with 2a x1 is equal to d ln gamma 2 by dx1. So now let's say I am integrating this. So when x1 is equal to 0, this thing we have seen, right? When x1 is equal to 0, my gamma 2 is equal to 1. Correct? Sorry, where did it go? Huh. When x1 is equal to 0, my gamma 2 is equal to 1. When this component is in infinite dilution case, very little, so other component is automatically in excess. So if that excess, the quantity, the component that is in excess will behave ideally. So gamma 2 will be equal to 1 to any x1 to any gamma 2. Okay. Okay, so we are left with this integral of differential of ln gamma 2 will be just ln gamma 2. So we have ln gamma 2 minus ln gamma 2 is equal to 1. So ln gamma 2 minus ln 1. So ln 1 is 0. So this term we don't need. So we are just with ln gamma 2 is equal to, okay, 2a x1, integration of x1 is x1 square divided by 2. So 2 cancels out. So it is a x1 square limit x1, lower limit 0, upper limit x1. So we are only left with ln gamma 2 is equal to a x2 square. So what did we know? We find that if I know gamma 1, from this relation I can find gamma 2. So if I expressed ln gamma 1 is equal to a x2 square, so I find that my ln gamma 2 will be nothing but equal to a x1 square. So gamma 2 uh, is gamma 1 is dependent on x2, gamma 1 is dependent on x2, and gamma 2 is dependent on x1. Okay. So okay, so these things we find out. Okay, so let's try to have a look at some different way, and we will again touch this point of we'll again touch this. Where did it go? This part. So okay, so how can I find anyway activity coefficient? Let's say I'm performing one experiment. So I'm considering a closed system. Okay, so I'm considering a closed system which is consisting of liquid and vapor phase. Okay, so I'm giving some pressure to the system and allowing the system to stabilize or allowing the system to attain equilibrium. Okay, so when I will attain the equilibrium, so I will have at that equilibrium, I will have the values of x1 and y1. Okay. Now what I'm doing, I'm changing the pressure of the system and repeating the procedure. Okay. So for different pressure, VLE data can be generated. Okay. And I know that xi, gamma I, fi, f1 is equal to y1, f1 cap p. And when I am dealing with low pressures, so we can assume phi1 cap is equal to 1 and Poynting correction factor to be is equal to 1 and fi f1 I can replace with p1 set. Okay, so I have this term gamma 1 is equal to y1 into p divided by x1 into p1 set. So okay, so at some pressure, okay, I find out the values of x1 and y1. I note it down. Okay, this is called as f1 cap y1 into p. So y1 I find out, I noted it. Then x1 I find out, I noted it. Okay, here it should be x1. And then I will take the ratio. I'm so sorry. Yeah. So these terms I will be noting down, and from there I will be finding the values of gamma 1 and gamma 2. So what did I do? I performed some experiment where liquid and vapor is in equilibrium. I fix some pressure and try to equilibrate it, and for that particular pressure, I find out what is y1 and x1. And from that y1 x1, I can just take this y1 into p divided by x1 into p1 set, and I can find the values of gamma. And like this, I can find all values of gammas in case of all conditions. Okay, but this is very tedious way, and this took very much time. It is not easy to maintain the pressure. It is not easy to find out the composition when we are dealing with experiment, and I want to find gamma 1, gamma 2. Okay, so there is one more method, one other method, that is excess Gibbs energy method. So we know that G by RT is nothing but x1 ln gamma 1 plus x2 ln gamma 2. And we had a look at this part here. So the slopes, sorry. Yeah. So x1, if I am varying it with x1, so this is my G by RT. So when x1 tends to 1, so I will have ln gamma 2. When x1 tends to 1, so the component 2 will be in infinite dilution ln gamma 2 infinite. And when x1 tends to 0, I will have ln gamma 1 infinite that will try to approach this particular curves. Okay. Ln gamma 1, ln gamma 2. Okay. And we have assumed that both intercepts, when I am plotting this is just theoretical representation. So I have assumed that both the intercepts are same. Okay. So see, when I am dealing with positive deviation from Raoult's law, okay. So it will be intercepts will be differing. Okay, and when I am dealing with negative deviation, it will be lower side. So uh, it is this. Okay. So we find out that when I am plotting G by RT versus X1, so it is a curve. But when I am plotting G by X1, X2, RT, so it is a straight line. You see here. So similarly, if you see here, G by RT is this one curve. But when I am plotting G by X1, X2, RT, it is a straight line. This is positive and this is negative deviations. Okay. So what can I do? I had x1, y1, gamma 1, gamma 2, ln gamma 1, ln gamma 2. And G by RT curve I have, and I can, this G by x1, x2, RT is nothing but linear. If you see, no, it's not written here. Okay. So we know that from graph of G by RT versus x1, we know that when x1 is equal to 0, this is wrong. X2 should be equal to 1 here. So when x1 is equal to 0 and x2 is equal to 1, we have G by RT is equal to 0. But we find that G by x1, x2, RT is a linear curve. Okay. So this is straight line, this is positive deviation, and this is negative deviation. Okay. So how to model this? So there is one expression by Redlich and Kister. So before that, I want to show that expression. This ax2 square expression, what we were looking at, this azeotropic condition. So that is called Margule equation. If I remember it correctly, it is called Margule equation. So that is very easiest equation. A into x2 square ln gamma 1 is equal to a into x2 square, and ln gamma 1 is ln gamma 1 is equal to ax2 square, ln gamma 2 is equal to ax1 square. Very easy form of gamma 1 and gamma 2, but in reality it is not actually like that. So what did Redlich and Kister did? They did some expansion, power series expansion, and they wrote that G by x1, x2, RT is A plus V x1 minus x2 plus C into x1 minus x2 whole square, like that terms. Okay. Yeah, this term. Okay, so when B and C are equal to 0, so I will have symmetric intercepts, right? G by x1, x2, RT is equal to A. Correct. So G is equal to A, x1, x2, RT. So G is equal to A, N1, x1 is N1 by N, x2 is N2 by N, RT. So NG by RT is equal to A, N1, N2 by N. So if I differentiate this equation with respect to N1, so see, let's have a look at it again. So for this power series expansion, let's say B is equal to 0, C is equal to 0. So I will have GE is equal to G by x1, x2, RT is equal to A. So GE is equal to A into x1, x2, RT. So now I can replace x1 with n1 by n, x2 with n2 by n. So I can write down n, 1n I am taking here. So n into Ge by RT is equal to A n1 n2 by n. Okay. Now if I'm differentiating this equation with respect to n1, so what is it going to be? I am keeping A into n2 out because n is equal to n1 plus n2, correct? It will be a complex equation. So if I keep this denominator, yeah, okay. So let's say I'm first keeping n2 constant. Yeah, n2 is n minus n1. So that differentiation will be minus 1. And if I keep n1 constant, differentiation of, yeah, okay. So this will give us, so see, denominator square is already written. So first let's say n1 is constant. So differentiation of n2 will be is equal to, which is n minus n1. So minus 1 plus n2 constant, differentiation of n1 will be just 1. Yeah. Okay. So from here, you can write it down as A into x2 square. Okay. So n, and we know that this del NGE by RT with respect to del N1, this term, del of NGE by RT by del N1 will give me ln gamma 1. So ln gamma 1 is nothing but A into x2 square. Similarly, ln gamma 2 will be is equal to A into x1 square. So this equation, very simple form of equation, this is called as one parameter Margule equation. So how did we derive? We derived it from Redlich-Kister expansion, where we took b is equal to 0 and c is equal to 0 and all meaning all intercepts are same. So in this case, we derived this equation ln gamma 1 is equal to ax2 square and ln gamma 2 is equal to ax1 square. Okay. So this is called one parameter Margule equation. And when I am dealing with infinite dilution, so any of that x1 tends to 0 or x2 tends to 0, I will be having intercept A is equal to ln gamma 1 infinite or ln gamma 2 infinite if we see from here. So intercept is nothing but when I am dealing with infinite dilution, intercept will be ln gamma 1 infinite or ln gamma 2 infinite and both intercepts will be same. Okay. Yeah, x1 tends to 0, graph of ln gamma 1 versus x1 shows ln gamma 1 infinite. Now, when I am dealing with asymmetric intercept, we have not derived the equation for that, but that will be something. Okay, let's try to formulate the problem. So let's say I'm dealing with asymmetric intercept. So now I am considering one more term b. I'm not considering c. C is equal to 0. I'm keeping. So the more term you are going to take, the more accurate your predictions will be. Correct. So g by x1 x2 rt is equal to a plus b x1 minus x2. Okay. So I can write it down as here b is a is multiplied with 1. So which is x1 plus x2 is equal to 1. So I'm writing a into x1 plus x2 plus b into x1 minus x2. And if I expand it, ax1 plus bx1 plus ax2 minus bx2. So it is a plus bx1 plus a minus bx2. So that is nothing but this a21 x1 plus a12 x2. Okay. So this is GE by x1 x2 RT is equal to A12 x2 plus A21 x1. Okay, so where A12 is A minus B and A21 is A plus B. We will have these conditions. X1 tends to x2 tends to 0. We will have ln gamma 2 infinite, which is equal to A21. And when x1 tends to 0, we will have this conditions must satisfy in whatever equation or whatever form we are writing, this must satisfy. So when x1 tends to 0, so we will have ln gamma 1 infinite will be A12. Okay, when we are dealing with asymmetric intercept. And in similar way, when I try to derive this equation, so I find it out as ln gamma 1 is equal to x2 square A12 plus 2 A21 minus A12 x1, and ln gamma 2 is equal to x1 square A21 plus 2 times A12 minus A21 x2. Okay, so this is known as two parameter Margule equation. Okay, so one parameter Margule equation was very easy. Ln gamma 1 was equal to A into x2 square, ln gamma 2 is equal to A into x1 square. And two parameter Margule theory, we considered this both the slopes A and B, first two slopes, and from there we try to find out this interactions parameter. We try to find out ln gamma 1, ln gamma 2 in terms of this x2 square, and limiting criteria must satisfy in whatever equation we are writing. When x1 is tending to 0 or x2 is tending to 0, this thing should be satisfied. Okay. When x1 is tending to 0, so this term is going to be 0. x1 tending to 0 meaning x2 tending to 1, so this is 1. So we are only left with A12. So A12 will be gamma 1, ln gamma 1 infinite when I am dealing with x1 tending to 0. Similarly, when x2 tends to 0, so this term is going to be 0 and x1 will be 1. So this term is also going to be 0. So ln gamma 2 will be gamma 2 infinite will be equal to A1. So this equation is known as two parameter Margule equation. Okay. Now there are various equations available. So there is one more equation, Van Laar equation. The one form we try to study, but this is in some different way. Okay. So here we expanded G by x1 x2 RT, correct? G by x1 x2 RT. But what Van Laar did, he tried to expand x1 x2 RT by G. So he wrote it as x1 x2 divided by G by RT is equal to A prime plus B prime x1 minus x2. Similarly, A prime is multiplied with 1. So let's say it is x1 plus x2. So I have A prime plus B prime x1 plus A prime minus B prime x2. So I can write it down A prime plus B prime as 1 upon A21 prime and A prime minus B prime as 1 upon A12 prime. So I can write down x1 x2 divided by G by RT is x1 by A21 prime plus x2 by A12 prime. Okay, now it is this cross multiplication A12 prime x1 plus A21 prime x2 divided by A12 prime A21 prime. Okay. So if I reverse it, G by x1 x2 RT is nothing but A12 prime A21 prime divided by A12 prime x1 plus A21 prime x2. And when I am solving this equation the previous way that we did, very simplest way, in case of Margule equation when we did it, yeah. So the way we did it, we can also do it in case of this Van Laar approach, but it will be more complex. So the final equation, you find it out in terms of like this: ln gamma 1 is equal to A12 prime 1 plus A prime A12 prime x1 by A21 prime x2 raised to minus 2. Ln gamma 2 will be equal to A21 prime 1 plus A21 prime x2 divided by A12 prime x1 raised to minus 2. Okay. Now when x1 is equal to 0, this term is going to be 0. So this whole term is going to be 1. So ln gamma 1 infinite will be A12 prime. And when x2 tends to 0, so this term will be 0. So this whole term in bracket will be 1. So I will have ln gamma 2 infinite is equal to A21 prime. Okay. And this this Van Laar equation is approximately superior, slightly superior than Margule equation, and this equation generally matches well with experimental data. And the limitation is this whole equations, this can be only used for binary system. We cannot do for ternary system. How are you going to define the equations when we are dealing with ternary equations? So ternary systems. So this is only for binary systems. Okay. So now, okay. So how can I calculate this constant? This we have studied earlier. Let's say I'm dealing at azeotropic conditions. Okay. So we know that from modified Raoult's law, y1 into p is equal to x1 gamma 1 p1 set. And as at azeotropic condition, we know that y1 is equal to x1. So gamma 1 azeotropic will be equal to p by p1 set, and gamma 2 azeotropic will be equal to p by p2 set. Okay. So if I take the ratios of ln gamma 2 by ln gamma 1, so we will have this kind of some equation, correct? And if I simplify these equations, we find that at azeotropic point, x2 ln gamma 2 by x1 ln gamma 1 is equal to a12 prime x1 divided by a21 prime x2. I will just keep the screen open. So what I did, I just took the ratio ln gamma 2 by ln gamma 1. Okay. So this term divided by this term. Okay. So then I multiplied it a12 prime x1 plus this divided by a12 prime x1. This thing. Okay. Now these terms are same. Numerator is same in both cases. So I'm only left with this 1 upon a12 prime x1 minus 2, 1 upon a12 prime a21 prime x2 minus 2. Okay. So similarly, I can write it down. Then if I simplify this, I get this condition of azeotropic point in case of Van Laar equation, which is x2 ln gamma 2 by x1 ln gamma 1 is equal to a12 prime by x1 divided by a21 prime by x2. Okay. So if I put this equation 7, a12 prime x1 divided by a21 prime x2, this term if I replace, so I get ln gamma 1 with this term, x2 ln gamma 2 by x1 ln gamma 1. If I replace it, so I get a12 prime is equal to ln gamma 1, 1 plus this term square, and a21 prime when I'm replacing this term in second equation. So I get this term, okay, ln gamma 2, 1 plus x1 azeotropic by x2 azeotropic and n by ln square. These azeotropic conditions are, if are known, you can easily find out constants. Similarly, when we dealt with this, we deal with this two parameter Margule equation. Similar thing we can also do here, right? That ln gamma 2 by ln gamma 1 is equal to this term divided by this term. Okay, I have not done it, but for this two parameter Margule equation also you can find it out. Okay. But it is not as straightforward as it is looking. Yeah. Okay. Now, these are some models we learned from Redlich-Kister model. We first find one parameter Margule model, two parameter Margule model, and Van Laar model. And for Van Laar model, we try to find out A12 and A12 prime and A21 prime with azeotropic condition. Now there are some more generalized model available in the literature. So each model have their own benefits and own drawbacks. So this first model is known as Wilson equation. So Wilson express the main term is this term, right? How we are expressing our G by x1 x2 RT term. So Wilson, he expressed G by RT as minus x1 ln of x1 plus x2 gamma 1 lambda 1 2 minus x2 ln x2 plus x1 lambda 2 1. Okay, so from there, if you know G by RT, then following this tedious process, you can find out the ln gamma 1 and ln gamma 2. So for Wilson equation, ln gamma 1 is this minus x1 minus of ln x1 plus x2 lambda 1 2 plus x2 this term lambda 12 by x1 plus x2 lambda 12 minus lambda 21 x2 plus x1 lambda 21. This term is same in both the cases. Both the means when I'm dealing with ln gamma 1 and when I'm dealing with ln gamma 2. Okay. Now if I want to write this equation in terms of multi-component system, okay. So it will be just here one more term x3 ln x3 lambda 13 will be added. Here also one more term will be added, and here minus x3 and some more term will have. So you understand that how complex it will be when we are dealing with from binary to multi-component systems. Okay. So this is some general term. So this lambda is nothing but we can find it out in terms of this interaction parameter. So this lambda contains this molar volume terms and Vj by Vi exponent minus Aij by RT. So I don't know if Smith-Warnes is having these constants, but we can have a look. So this you can know how this A12 A21 looks like. Okay, it is not given, it is only given for UNIQUAC model. So if we see Wilson parameter stable. Okay, if we see Wilson's parameter table, so it looks like this. Yeah, see, it looks like this. When I'm dealing with methyl acetate system, so this A21 and A12 I have. Similarly, methanol, methyl acrylate system, you directly have these terms. Sorry, where did it go? You have this term A12, this A12 and A21 is there. Then from there, you need to find VJVI, molar volumes are known from literature. So you can find this lambda parameter, and if you put it here for given x1, x2, you find gamma 1, gamma 2, and from that corresponding gamma 1, gamma 2, you need to do y1p is equal to x1 p1 set, x1 gamma 1 p1 set. So from there you can use this vapor liquid equilibrium. Okay, so this is how messy it looks like. So what are the when can we use Wilson equation? So Wilson equation can be used for components those differ from each other in the molecular size. Then intermolecular interactions between like and unlike molecules are different. In that case, we can use Wilson model, and Wilson model predicts the temperature dependence of gamma 1 and gamma 2. Okay, so if I change the temperature, let's say this equation lambda 12 is equal to V2 by V1 exponent minus A12 by RT. So if I change the temperature, so this lambda 1, lambda 2 is going to change, and gamma 1 is also going to change. So this says that gamma 1, gamma 2 are function of temperature when we are dealing with Wilson equation. So this is not applicable to the systems when ln gamma 1 exhibits minima or maxima, and it is unable to predict the limited miscibilities. Okay. Okay. Now there is one more model that is known as NRTL model, that is called non-random to liquid theory. So in NRTL model, G by x1 x2 RT is expressed by this equation G12 tau21 divided by x1 plus x2 G21 plus G12 tau12 divided by x2 plus x1 G12. And G12 is exponent of minus alpha tau12, G21 is exponent of minus alpha tau21, and tau12 tau21 B12 by RT, B21 by RT. So if we see here, so we have one additional term alpha when we are dealing with NRTL model. Okay. and B12, B21 are always there. B12, this is similar. I am right. Here we have written in terms of A12, so it is same only. So A12, A21 is here, and this is alpha term. So alpha term is additional. So this also captures the temperature dependence of gamma. Okay, so let's say I'm finding at some temperature 298 Kelvin. So I will first find out from literature. Let's say I'm dealing with this system, methanol, methyl acetate. So I have A12, A21. So I will put A12, A21 here, and at particular temperature, I will first find tau12, tau21. Then I will put it here, and for that particular alpha, alpha is there 0.27101. So for that particular alpha, I will find G12, G21, and I will put this whole G12, G21 and tau21, tau12 here. And I will find ln gamma 1, ln gamma 2, and this is dependent on the value of temperature that we are choosing. Okay. So this is non-random to liquid theory, NRTL model. Okay. For various systems, these constants are available in literature. Okay. So now there is one more model. This is called UNIQUAC model. So it is universal quasi-chemical equation. So this UNIQUAC model that was developed by Abrams and Prosnitz to express the excess Gibbs free energy of binary mixer. So G by RT, the term from where we are finding this activity coefficients gamma 1 and gamma 2. It is containing two parts, combinatorial part and residual part. So I can write it down G by RT as G by RT as G by RT combinatorial part plus G by RT residual part. Okay. So this combinatorial part, it takes into account the composition, size and shape of the constituent molecules and contains pure component properties. So it is only dependent on pure component properties, and it takes into account the composition, size and shape of the molecules. Okay. The residual part, it takes into account the intermolecular forces, and it contains two adjustable parameters. Okay. So if you see combinatorial part, it is this summation I xi ln phi by xi plus z by 2 summation I xi qi ln theta I by phi. Okay. What is phi? Phi segment or volume fraction of that particular component I. Theta is area fraction of that particular component I. Ri is volume parameter of component I. Qi is surface area parameter of component I. And for this residual part, tau gi is exponent of this parameter minus ugi minus uij divided by RT. Okay, and this UGI is average intermolecular energy for the interaction of molecules of component I with the molecules of component C. And Z is generally coordination number, and it is taken as 10. So from this was combinatorial part and this is residual part. And from this, ln gamma 1 is ln gamma 1 combinatorial plus ln gamma 1 residual. Okay. So this is combinatorial form. This is very complex. It looks very easy, but it is not. So this is combinatorial part and this is residual part. Okay. So if you open, I guess this book has. So see, no, this is UNIFAC, not UNIQUAC. Okay. So UNIQUAC model. So see here, A1 to A21 is there. These parameters we need to know. In case of UNIQUAC model, see A1 to A21 here in this particular term. Here we need to know A12 and A21. Okay. Now So see, these are R and Q parameters that we first need to find out. We first need to find R and Q. From R and Q, we find L, and this L we put here, phi and phi theta, we find it from here. Okay. So this is very complex. It looks very easy, but it is not. So generally, experimental data is available. So for that particular experimental data, we try to use this various model and we see that which model is giving the best result. Okay. UNIQUAC is applicable to a wide variety of liquid solution, but it is mathematically more complex. Okay. So what are advantages of using UNIQUAC? It contains only two adjustable parameter A1 to A21 instead of three parameters in NRTL. Those are less dependent on temperatures also. And UNIQUAC is applicable to solutions containing small as well as large molecules. Okay, so these are benefit of UNIQUAC model. UNIFAC is not here, but there is one more model which is known as UNIFAC model, which is widely used in any system for any systems. Sorry, where did it go here? There also it is combinatorial and residual part. Okay, but there are some slight changes in the equations. Okay, so that we will not worry about right now. Okay, it is nothing but UNIFAC is nothing but activity group contribution kind of thing. So where you have each groups contribute something, CH3, CH2, CHC, all each of these groups contribute to final activity coefficient value or final predictions of vapor liquid equilibrium. Okay, now okay, so this was all about today's class, but let's try to okay, and one more thing, what does UNIFAC and all other models assume? So you see that here there is one functional group CS3. So CS3 is contributing some R values and K values. So what is it assuming? It is assuming that CS3 is same for everything. So if I'm doing methanol, so CS3 is going to be same. If I'm doing ethane, CS3 is going to be same. It is not going to change. Okay. UNIQUAC is widely used model from the literature. Okay, so now, okay, so these all things were very complex. So let's try to have a look one more time. What did we do today? Basically with non-ideality part, just give me a minute. Okay, so let's first try to revise what we did today. So we started with in today's part, this was very heavy lecture for today. So let's try to go through quickly what we did. So we first tried to study the modified Raoult's law, which includes the activity coefficient or correction parameters to the non-ideality for the liquid phase. Okay, so it is nothing but y1 into p into phi1 cap is equal to x1 gamma 1 FIL, and for low to moderate pressures, this yi into p is equal to xi gamma I pi set we find, and this is known as modified Raoult's law. Further, we find bubble point and dew points from this modified Raoult's law. Then we did very basic of this flash calculation using modified Raoult's law. Then we had a look at how to find gamma values. Before that, we had a look at this very important phenomena: excess properties, actual property minus ideal properties for VE, HE, UE. For Gibbs free energy, excess Gibbs free energy, it is nothing but summation xi ln xi, and partial molar excess Gibbs free energy is RT ln RT summation ln gamma I. Okay. From there, we find the dependence of temperature and pressure on activity coefficient. Then we've tried to derive the Gibbs-Duhem equation in terms of activity coefficient. Yes, we try to derive that. Then further, from the Gibbs-Duhem equation at constant temperature pressure, we know that x1 dln gamma 1 plus x2 dln gamma 2 is equal to 0. And from there, we see that slope of ln gamma 1 versus x1, it is opposite to the slope of ln gamma 2 versus x1. And when x1 tends to 0, for the other component, it behaves ideally. So ln gamma 2 tends to 0 and x1 tends to 1 and ln gamma 1 tends to 0. And we try to see that if I know the gamma 1, I can easily find the value of gamma 2. And for that, we took one example, ax2 square, when I express ln gamma 1 in terms of ax2 square. From there, I can find ln gamma 2 is equal to ax1 square. Then we talked about a lot about gamma 1. So we tried to have a look at how to find activity coefficient. So there is one simple experiment, vapor liquid equilibrium. So from there you need to note y1, y2, and you can find gamma 1, gamma 2 using this particular expression. But this is a very tedious work. Then there is one excess Gibbs free energy method which express G by RT as x1 ln gamma 1 plus x2 ln gamma 2. And this partial GI by RT, this we have a look ln gamma I. And we see that slopes can be same, both intercepts can be same or intercepts can be varying. Okay. Then we expressed Redlich-Kister expansion using G by x1 x2 RT as A plus B x1 minus x2 plus C x1 minus x2 whole square. When I am dealing with symmetric intercepts, I took B and C as 0. So I only have this particular term and I find out that ln gamma 1 is equal to ax2 square and ln gamma 2 is equal to A into x1 square. For asymmetric intercept also, and this particular equation is called one parameter Margule equation. Similarly, when I included two terms A and B, so I have this kind of equation, two parameter Margule equation, x2 square a12 plus 2 a21 minus a12 x1, and similarly for ln gamma 2. Then we express Laar equation. So what he did, instead of doing power series expansion of GE by x1 x2 RT, he did x1 x2 RT by GE. And he tried to find out something like this equation. Okay. Then we tried to find out azeotropic condition. Further, we had a look at very complex models. One of that is Wilson equation. So this was the Wilson equation, very complex. Then NRTL, non-random to liquid theory model, which had A12, A21, tau12, and G12 alpha, so many terms. Then further complex equation, that is UNIQUAC model. So it has G by RT, two terms, combinatorial part and residual part. And combinatorial part takes into account the composition, size and shape of the constituent molecules, and it contains pure component properties only. Whereas the residual part, it takes into account the intermolecular forces and contains two adjustable parameters. Okay, so this was all about UNIQUAC model. Okay, so let's try to have a look at some problem statements that we are not able to look for so long. So we are left from this particular problem. From here we are left. So the question is, determine the vapor pressure in kilopascal for liquid n-hexane at 0, 30, 60 and 90 degree Celsius using constants. Okay, so we are first dealing with n-hexane molecule. So How can I find out vapor pressure? This was some classes ago. I'm closing these slides. It is not required. Okay, so we had this equation. So let's try to have a look at this table. So in this Smith Warnes book tables, in appendix, some tables are available. So if you see here in index, so you can see this whole appendix, A, B, C, D, and all. So I need to find out these properties of pure species. Okay, so this is the Antoine equation, right? So in this there are various ways how Antoine equation is defined. So this one equation is ln p set is equal to a minus b divided by t plus c. So where temperature is taken in degrees Celsius and pressure is taken in terms of kilopascal. Okay, so we are supposed to find this 4 molecule n hexane. So okay, so if I try to find out n hexane from here, so where is n hexane? Here, this is n hexane. Okay, so for n hexane, we know that these are ABC parameters. Okay, so A is equal to 13.8193, B is equal to 2696.04, and C is equal to 224.317. Okay, and ln p set is equal to A minus B divided by T plus C. So A is 13.8193 minus B, that is 2696.04 divided by temperature in degrees Celsius plus C, that is 224.317. Now I am supposed to find this P1 set, P2 set at 0 degrees Celsius, 30 degrees Celsius, 60 degrees Celsius, and 90 degrees Celsius. Okay, so what I need to do, I just need to put the values 0, 30, 60, and 90 here, and I can directly find out the values of P1 set. Okay, one thing we should note here that when we are dealing with this this bubble point, dew point computation, so in problem, let's say you have to deal with methanol water mixture. So you will not be generally given in your examinations. You will not be given in your this examination. It will be given, but actually you should know how to find out this constant. So from this book, James Smith, you can see from here that for various components, acetone, acetic acid, acetonitrile, butanol, various components, this ABC constants are available. So for whatever component you are dealing with, you should find these ABC parameters from here. You need to put ABC here, and for whatever temperature you are dealing with, for whatever temperature you are working with, you need to put the value of that temperature here, and you can find out the value of P1 set, P2 set, whatever the mixture is. So this is something you must know. Okay. So this is how you can find out these Antoine constants, ABC. Okay. So let's stop it here. Today was very heavy class. So further we have so many problems remaining, this partial molar properties problem. So this we will try to solve in upcoming classes. Uh, one more thing. Okay, so if anyone is having just a minute, if anyone is having any query regarding thermodynamics or anything else, please feel free to please feel free to write to me on this particular email ID. I will try to respond to you as soon as possible. As soon as I can, I will try to respond to you. So thank you so much. We will meet next class. We will meet on next class.